In our project, we are trying to simulate the vapor condensation and recirculation back as reflux to a distillation tower and put up a control systems that allow us to control the reflux to a distillation tower and also the level in the reflux drum. The overall process, we have a tower where leaving the top will be a vapor, which then goes into a condenser where we completely condense into a liquid. And then that liquid feeds a reflux drum. And then this reflux drum material, part of it will get returned through a reflux loop to go back to the top of the tower. And the remaining portion will be taken off as distillate. And what we want to do is control the reflux rate going into the tower using a control valve, and also the level of liquid in our reflux drum using the control valve on our distillate flow. My particular example, I'm running a tower at 2 atmospheres of pressure. The tower height is 50 meters, and I'm using water as my fluid, which exits my uh, tower at 2 atmospheres of pressure. We condense at 2 atmospheres. Therefore, our fluid going through our reflux drum and downstream piping will be water at its bubble point. We can do some initial estimates as to what we will need to specify on this project. And the one key thing is we have a pump that not only supplies the reflux to the top of our tower, but also our distillate. And to estimate what that outlet pressure of our pump would be, we can quickly do some rough calculations to predict that. If I look at just the portion of the stream that goes up and into the top of the tower, I have to consider various portions of this stream. One is the liquid coming into my tower must be at the tower pressure, which is 2 atmospheres. If it's less than 2 atmospheres, then we won't be able to get flow into the tower at that point. I also have to overcome 50 meters of elevation change, so that will result in static head. I have to overcome some friction losses due to a control valve and also some piping frictional losses. So let's estimate how that will be. In terms of static head, we have liquid water, and I'll use 1,000 kilograms per cubic meter as its density. And multiplying the density times the acceleration of gravity times the height of the liquid, we end up with a 490,000 pascals of pressure, which is 4.8 atmospheres. Heuristics tell us that a typical pressure drop across the valve is 0.7 atmospheres, which is equivalent to 10 psi for good control. And through the piping, I'm going to allow some pressure drop across those fittings and globe valves and check valves. I'll just use an estimate of about 0.5 atmospheres for the rough calculations. We'll have ChemCAD do the exact calculations for us. So when I look at on the outlet of my pump, I have to overcome my frictional loss through the piping. I have to overcome the frictional loss across the control valve, the frictional loss and elevation change going up to the top of my tower. Plus, I need it to be 2 atmospheres of pressure. So that outlet pressure, I just sum up and we end up with about 8 atmospheres leaving my pump. Now our tower is operating at 2 atmospheres and we'll assume very little pressure losses through the reflux drum and the pipe feeding my pump. Therefore, the inlet pressure should be pretty close to 2 atmospheres of pressure. Therefore, the increase in pumping, I'll go from 2 atmospheres of pressure to 8, so my pump pressure increase would be 6 atmospheres. My total flow going through my pump is set at 308 gallons per minute as my normal flow rate. And in my particular case, I'm going to split that equally 154 gallons per minute for the reflux and 154 gallons per minute for the distillate flow. When we size for piping, if we do not have a maximum flow given to us, we'll just increase the normal flow by 30%. So for the reflux line, I'm going to multiply 154 times 1.3, and I'll have 200 gallons per minute going to the top of my tower. Similarly, for my distillate, it's also 154 gallons per minute times the 1.3, or 200 gallons per minute for the distillate flow. And the sum of these two flows must be the material equal to the material flow coming in to my pump. So I'll have to size for 400 gallons per minute for the feed. Therefore, I can now start to use some of the features of ChemCAD that will allow me to do these calculations. If you're starting from a clean flow sheet, I recommend that we break this into small pieces, make sure that we fully have each piece working properly before we add another element to the flow sheet. So for starters, we would have a feed going into a dynamic vessel. And in my case, in my case, imagine that I have a flow coming out of it as a product rather than feeding another element in there. So the dynamic vessel would be my reflux drum. The outlet at the top of this would be for any vapor that may be flowing into my process or coming in with this stream, and the outlet flow would be liquid. My feed flow is liquid water at its bubble point. Now my stream is 2 atmospheres of pressure, but I don't know what the bubble point temperature is. An easy way to find that out would be, if I don't know that temperature, I'll just leave that blank for right now. I'll just put in 1 for the vapor fraction and flash it. And it tells me that the dew point temperature is 120.629. And I can just specify my temperature at 120.62 and hit flash, and that will be a liquid right near its bubble point temperature. I'm dealing with water, and by selecting the compound unit as weight percent, I can find a convenient unit to use would be the standard liquid gallons per minute unit, and I can type in 400. You would type in the flow rate of the chemical that you desire, and I would click OK. Now, like I said, imagine this stream coming out would be connected to a product arrow. And so I need to determine the size of my reflux drum first so that I know exactly what the levels are in this. So if I click on the reflux drum, just a single click, and go to the sizing menu, and we have choices for vessels. I have a liquid and vapor vessel. There's only one liquid phase, and I would select that. Heuristics tells us that reflux drum are almost always horizontal, so I would select that button, click OK, and then it will use a length to diameter ratio of 3, which is a heuristic value. The minimum retention time is 5 minutes at half full, so I'll use that value and click OK. And it immediately calculates that the inside diameter of my vessel should be 1.6764 meters and a length just over 5 meters long. And ChemCAD will actually put those values into our dynamic vessel. We would have horizontal, the diameter be 1.6764, and the cylinder length 292 meters. The initial charge, we will put right now the initial liquid level at half the height, which would be the half the diameter of our vessel, 0.8 meters. We're going to have a fixed pressure that will be equal to my column pressure, in my case 2 atmospheres. I will select the box that tells me to include the liquid static head pressure in the output streams, meaning in stream number 2, in my case, it will be the 2 atmospheres of pressure in the vessel plus whatever that zero point 0.8 meters of liquid level would be exerting on the bottom of that. In terms of the outlet flow, for right now, we'll just say it's at a constant level, and we'll say that level will be 0.8 meters. And that would be all the numbers we have to select. The other thing is telling it, well, what's inside this vessel at the beginning? And there's an option that gives us from the outlet stream composition as the initial charge. Meaning this, if that's selected, I can enter the conditions for stream 2, and it will use that for the initial charge. So I would click OK on that. And then I would enter the initial conditions for that stream. If you recall, we had the pressure of the vessel was at 2 atmospheres, and we don't know exactly what the static head would be. So the first guess, we would just put in 2 atmospheres of pressure and 120.62 as our temperature. And I will just put in a known composition. I know it's water, 100%, and the total flow rate will put at 400 gallons per minute. But that flow rate doesn't come into play for that initial charge. So what it will do is use those stream values and use that as the composition for what's inside my vessel. So if I just run that particular unit up, then it will immediately calculate in stream 2 that our temperature is 120.625, and instead of 2 atmospheres, it's now 2.073, and that's because that height of the liquid added a little bit more pressure at the bottom of it. So that's how we would use the stream leaving it as the main way of determining what the composition and temperature is inside my vessel. Leaving my vessel, I have a pipeline that's going to feed my reflux pump. And in this pipeline, I need to determine what's the proper size. If I know the flow rate coming out of this stream, okay, right now it's 400 gallons per minute, 100% water, and its temperature is 120.625. I can use a feature in ChemCAD, just single click on the line you want to size, go to my sizing menu, and what I want to do is size a pipe, and we are going to size for stream 2, and I'll click OK. And here are the options. We'll say that it will be a typical sizing for a single phase. Schedule 40 is a common schedule for piping, and the roughness factor, 4.572 times 10 to the minus fifth, would be the roughness for commercial steel, and I would click OK. and it would do the calculation for me what the nominal diameter should be, 0.127 meters, and what the pressure drop will be, what the liquid velocity would be. In this case, it calculates it at 2.1 meters per second, which is pretty close to what heuristic values are. Another way I could have done this is inserted a pipe unit op from the ChemCAD palette and go to the sizing menu for that pipe and click on the pipe and select the stream and click OK, and it would immediately go to the same menu and give me the results I wanted. Okay, a third way of doing it, if you right click on the stream and hit pipe sizing, gives you the same kind of menu. So we have many options to use for calculating the pipe diameter it recommends. So based off of that, I'll use that nominal pipe diameter for my pipe. Okay, and so I'll have a point or 0.125 meters or 125 millimeter pipe, which is a 5-inch pipe in my case. The length will be 5 meters. We are told that we have 3 meters of pipe distance from our reflux drum to the point where we would branch off and have one leg go to one reflux pump. A second leg will go to a backup pump or spare pump. So we have a total pipe length of 5 meters. The change in elevation is -3 meters. My pipe material is commercial steel. If I look at some other elements in my pipeline before my pump, we will actually have 2 globe valves present. And under fittings, I'll have a standard elbow and a T where the flow comes in through the branch, and click OK. And if I run my pipe after that, I get a pressure 2.09 atmospheres, and my flow rate would still be the 400 gallons per minute, and click OK. We determine what the pressure increase is for my pump. So if I double click on this pump, I'll say specify pressure increase of 6 atmospheres. Heuristics will tell us about efficiency of 0.75 is appropriate, and it will calculate the outlet pressure, and click OK. So if I run my pump, I find that I'm right at 8.09 atmospheres of pressure leaving and at the flow rate that I desire. We have a small length of pipe that goes before we split off into 2 streams. This pipe has the same diameter as the inlet because I've sized it for that particular flow. So it's going to be the same inside diameter, 5-inch scheduled pipe, or 5-inch nominal pipe diameter, 40 scheduled pipe, and my pipe materials commercial steel. We have a couple other elements I have to put in. We have a globe valve to isolate my pump if needed, and we also have a swing check valve such that we don't have flow coming in the opposite direction. In terms of fittings, at this point, all we have is a flow out branch for the T, and that will go into uh, uh, the 2 legs of my outlet here. So we have that done, and I'll click OK, and I can run this unit up here and come out with a pressure of 7.939 atmospheres. Now we're going to split my flow. I want 200 gallons per minute coming out into each leg. I put in a divider, and I'm only going to specify one stream. I split it based on the flow units defined below. And my drop-down menu, I can use liquid gallons per minute at standard temperature and pressure, and I'll put it flow rate at 200. So if I run my divider, we'll end up with 200 gallons per minute flow going in one direction and 200 gallons per minute of flow going in the other direction. We'll go through a length of pipe before my control valve that regulates my reflux flow. So I will specify that particular case. It's going to be a Schedule 40 pipe, but I have a smaller pipe size, and that's because only have 200 gallons per minute flow instead of 400. So I would use the same sizing that a procedure I did before, and it would determine that the proper size would be 3.5-inch pipe. We'll have a length of 2 meters. We have a globe valve on the downstream side of my pipe and no fittings there. I'll click OK. In a similar fashion, the pipe going as my distillate, again, it will be the same diameter because I also have 200 gallons per minute. It will actually go through a 1 meter elevation change based off of the original diagram. And we'll have a globe valve present and a standard elbow. So this will allow it to go up 1 meter and then will go horizontally. I can then put in a control valve, but I need to know what would be the size of that control valve. So I have to use a sizing menu. But to use the sizing menu, I'm going to need to know what would be the downstream pressure of this. Well, the downstream pressure would be that 2 atmospheres plus that 4.8 atmospheres due to the elevation change, and maybe approximately a zero point 0.2 atmospheres of pressure loss through the piping. So I can estimate that the downstream pressure should be on the order of about, say 6 atmospheres. So if I right click on the stream leaving my pipe and put in control valve sizing, okay, and I said 6 atmospheres, I meant to say 7 atmospheres. We have 2 atmospheres plus 4.8, which makes 6.8, and then add an additional 0.2. Say the downstream pressure is 7 atmospheres. Click OK. And it calculates us a valve coefficient we would need for that 200 gallons per minute flow to be a value of 60. And ChemCAD recommends that the valve coefficient for 100% open would be a value of 124. Let's look at that a little more closely. Based on my 200 gallons per minute, which is actually the high end of my desired, I really shooting for is 154 gallons per minute. But at 200 gallons per minute, the valve opening, which would be the ratio of 60 over 124, is 0.4847, meaning at that high flow rate, my valve is going to be less than 50% open, Well, that would be quite an oversized valve because I'm going to be actually flowing at a value of around 154 gallons per minute. So I will actually put in a smaller recommended valve than that 124. So if I go to my actual valve specification, we have 124. Going to have to calculate what that would be. Okay, so if I have a valve coefficient at 60.1 at the full flow, which is 130% of my desired flow, I want that valve to be around 80% open. So I can calculate what that valve coefficient should be. So I want the total flow valve coefficient to be at a value such that 60 would be 80% of that. So if I take 60 and divide it by zero point 0.8, we get a calculated value of 75. So my valve that I'm going to put in, instead of it being 124, I'm going to select it to be 75 for that valve coefficient. Otherwise, it's going to be very, very large valve for the flows I want. We would choose a rangeability for a linear valve to be a factor of 1,000. My downstream pressure should be 7 atmospheres. And in the calculation mode, we're going to specify the flow, and it's going to calculate what that valve position would be. So we would specify flow and pressure, and it will determine what that number should be. Under controller options, we will put in a time constant of 0.2, which is common for control valves. It will give us a warning, but that is not an error. It just tells us we don't have a PID controller specified for that valve, and I'm okay with that. So if I run this particular valve and click continue, I determine that my flow is going to be 200 gallons per minute and my valve position 80.33%. And that's a good number to shoot for at that targeted maximum flow. Downstream of my valve, I have a length of pipe. Let's look at it. It's also going to be 3.5 inches in diameter for a 200 gallon per minute flow. Schedule 40. The elevation change is 50. It's going to have 50 meters of vertical distance that's going to go up. We have an additional couple fittings, so we'll have a 1 meter length before we go to an elbow. And then we have a valve at the top to isolate it from the column. So I will have 2 globe valves, one at the outlet of my control valve and one at the inlet to my column. And my fittings will have is 2 elbows. I'll have one here and one up here and click OK. So that will give me the flow and conditions going into my column. If I ran that particular unit, I would end up with a pressure almost the desired pressure of 1.96 atmospheres. Similarly, for my distillate, I'll have a length of pipe, and it will be also, in my case, 3.5 inch diameter because it also has 200 gallon per minute maximum flow. Schedule 40, it's going to go through an elevation change of 1, a pipe length of 2 meters. We have in it a globe valve to isolate it from the control valve here. And with the fittings, we'll just have a standard elbow. For the downstream valve, let me first size this valve using the flow rate going through the stream. I'll put in control valve sizing. Now I know the final outlet pressure of my distillate is going to be my tower pressure plus zero point 0.3. I will have a little bit of a pressure loss through this length of pipe, but I'll assume that it's small. So I'll say the downstream pressure is 2.3 and click OK. And it tells me that my valve coefficient should be 23 and the total valve is going to be 36. So at that 80% opening, or the maximum flow at 200 gallons per minute, we're only going to be 64% open, which is the calculated coefficient divided by the total capacity. We'd rather have that number closer to 80%. So if I take 23.12 or 13, divide that by 0.8, we should have a number close to 30 rather than 36. So I can click on my valve and use a value here of 30. Again, its rangeability would be 1,000. The downstream pressure is 2.3. We're going to specify flow and pressure, and it will calculate valve position. Again, we'll put in 0.2 for our time constant for my valve and click continue. And we can run my control valve, determine that its valve position is 77, which is fairly close to the 80% I calculated. And then lastly, we'll put on another length of pipe, which is going to be 1 meter in length, has a globe valve to isolate the control valve, and there are no fittings. So I systematically added these elements in, and you'll find that doing it that way rather than trying to put everything in and then trying to get this to work would be much more time efficient. So if I go ahead and run the entire program, we will see that coming out of as my distillate, I'm at 2.17 atmospheres. Notice that it wasn't the 2.3 that I wished, and that's because I guessed a value downstream pressure of this control valve to be 2.3. And so I should add a little bit more pressure there to overcome the pressure loss over this pipeline. So if I added, say, make it 2.43 in this case, and we run our program once again. Okay, very close to that 2.3. Let's check our stream coming into our column. It's 1.96, so I'm a little bit low here, and I can increase my downstream pressure of my valve, put in an additional 0.04 atmospheres. Click continue. Run everything. And I have it almost identically equal to 2.3 atmospheres, which will go into my column. I'm at 2.3 atmospheres leaving. I can check my total flow, 200 gallons per minute. And so now I have the layout for my process in terms of pipe specification and also what the control valve setting should be. And this will be useful when we go to putting in the dynamic system with the control valves. So this will assist you in getting your process together and be able to determine how your system would be when you're completing it. Good luck with this.